Hello everyone, welcome to what will be lecture 27. Obviously we are not in class and this is a video lecture, so you are still of course responsible for knowing this material, but we will get a start on the concepts behind thermodynamics today, and then we will continue that back in class on this Wednesday. Just some announcements and reminders. I obviously did not have office hours today, Monday, March 27th, but I will be back in my office on Wednesday, and anytime I'm there and my door's open, feel free to stop in. You can also, of course, email me to set up a time if you would like to meet specifically at a time. Homework 8 will be posted by the end of the day today. It'll be due on Sunday, and then we will have quiz number 8 on the following Monday, so a week from today. Please start studying now and let me know if you have any questions. And then the video key for quiz 7, as well as the quiz 7 token, will be posted after class, and then I will be returning those quizzes to you hopefully on Wednesday, assuming I can get back and get them graded by that time. Otherwise, I hope to have them to you basically ASAP. And I will be back on Wednesday, so if you do have any questions or would like to meet in person later in the week, please let me know. Okay. All right, so let's get into thermodynamics then, and we're going to start with a discussion of spontaneity. And so you may have noticed I've been using this word spontaneous throughout our electrochemistry chapter, but I didn't really take the time to define it, and so we're actually going to do that now. So spontaneous process is something that will occur naturally under certain conditions, and a non-spontaneous process will not take place unless it is driven. That's a term we often use in chemistry, as we have to drive things, in other words, put energy in from some sort of external source, some sort of other spontaneous process, in order to have that non-spontaneous process work. Okay? So an example of this that is technically chemistry, but on a larger scale, is think about a mountain lake. The water in that lake will naturally flow out of the lake downhill into a stream, but if we wanted to get that water back into the lake, we would have to basically have a pump that would pump the water back up the hill, or if nature were doing this, of course, we would get energy from the sun that would vaporize that liquid water into gaseous water, and it would eventually rain or snow into the mountain lake. But either way, we have to put energy in order to get the water back up to the top of the hill. Okay? Another example could be ice, and so ice is obviously just water, but if we have it at room temperature and pressure, it will spontaneously melt. However, if we put that water or an ice cube into the freezer, it will not melt. And so what you can notice there is we have a change in temperature, aka a change in energy, and that will cause a change in spontaneity. So just in case you didn't get it from the name thermodynamics, thermodynamic processes are often affected, or their spontaneity is affected by temperature, right? And something I should mention is that the spontaneity of a process has nothing to do with the speed of the reaction. That is what our unit on kinetics is for, that we're going to talk about at the end of the semester. But thermodynamics just has to do with the energetics for a reaction. Okay? And so another kind of example of this is we can think of allotropes of carbon. So we have diamonds and we have graphite. Both of these are just different arrangements of pure carbon atoms. And interestingly, graphite is actually the more stable compared to diamonds. And so a way we could describe that is if diamonds are our reactants, it would be thermodynamically favorable to turn them into products. And the reason they don't do that, of course, is we have this large barrier here. So you'll notice that the y-axis here is energy. We have to go up in energy in order to get over this hill before we can get to graphite. And so even though this would be a thermodynamically favorable process, the reaction does not normally occur because we have this barrier, and we're going to talk a lot more about that in kinetics. Okay? So next thing I want to talk about is how we think about this and how we think about thermodynamics on kind of the molecular scale with energy and matter. And so we often want to predict the spontaneity of a reaction, and that will help us know the tendency of certain systems. And so consider this flask below. If we have a closed valve and one side has a gas and one side is under vacuum, then if we were to open that valve, then there would be a spontaneous flow of matter from the side that has gas, that has pressure, to the side that is under vacuum, right? And so the way we would basically use fancier words to describe that is we would say that the matter moves towards a more uniform dispersal, meaning that we don't want one side with nothing and one side with a lot. We want both sides with essentially an equal amount, or a uniform dispersal of matter. If we wanted to reverse this process, we would of course then have to put energy in to recompress the gas back into one flask, and because we were putting energy back in, that would be a non-spontaneous process. Okay? The same thing is going to be true for energy. So the last example, of course, was matter. We could also think about this with energy. So say we had two objects, one of them is hot, one of them is cold. If we were to bring them together, we would transfer kinetic energy from the area of high concentration of energy, we could think of it, our hot object, to the area of low concentration of energy, right, or lower kinetic energy. And so again, we would say the system moved towards a more uniform dispersal, but this time of energy rather than of matter. Okay, so this gets us to the definition of what a microstate is. And so a microstate, the simplest way to think about it, it is one possible arrangement for energy or matter within a system. A macrostate is a collection of those measured properties, and those are the things that we most often observe. So things like temperature, pressure, and position are macrostates, whereas microstates is, as the name would imply, what is going on at a very small level. And so say, for example, we had an impossibly small flask that only had 4 atoms, and those 4 atoms could occupy basically or 2 atoms to a side, and they could occupy different positions. And so all of these would be different microstates, essentially, different arrangements of the atoms within those microstates. The more possible ways we can arrange things, the more possible microstates we have. And that leads us to basically entropy. So entropy is a term you may have heard before. If you have not, that is totally fine. I will define it right here as the measure of how the energy of a system is distributed. And so this was a concept kind of coined and discovered by Ludwig Boltzmann here. And so he actually gave us a way to calculate entropy of a system, and it uses Boltzmann's constant here, and then you just take the natural log of W, where W is the total number of microstates. And so we'll go through how to calculate that a little bit in the pre-lecture, and then in the lecture course on Wednesday. But key things to know here are that S is the variable we use to represent entropy, and the larger W is, basically the larger our microstates are, the greater our entropy is. And that is basically what was said there. One last thing with this that we'll talk more about on Wednesday is that the entropy of our system here, you'll notice this is an absolute value. And so in Wednesday, we'll talk about the delta S and delta properties, like which, in case you don't remember from first semester Gen Chem, when we put a delta here, that is signifying the change in something. But we actually know that entropy, S, has an absolute value, and that becomes significant for building out the rest of our understanding of thermodynamics. Okay, so that is it for our lecture for today. Hope it wasn't too burdensome, but if you do have any questions, please let me know. Otherwise, there will also be a pre-lecture posted tomorrow, which is Tuesday, for our lecture class on Wednesday, in which we will be back in the classroom together. Hope you are having a good start to your week. If you have any questions, please let me know. Otherwise, I will see you soon.